This video is going to cover a couple of the slightly more complicated questions you can be asked with arithmetic of complex numbers. I'm not going to go over addition, subtraction, or multiplication of complex numbers, but we're going to first look at an example looking at division, which should be fairly quick, and then look at when you might be asked to find the square roots of a complex number, which is a bit trickier. So if ever you're asked to divide complex numbers, so this is a classic example, doing 2 subtract 5i divided by 3 subtract 4i. The trick is always to find something to multiply the top and bottom by, which will get rid of any imaginary part on the denominator. And rather than having to search through that every time, what you're always going to want to multiply top and bottom by is the conjugate of the denominator. And by conjugate, we mean we're negating the imaginary part. Now, in this case, the imaginary part of our denominator is negative 4. So by negating that, we're actually going to make the complex number on the denominator 3 plus 4i. So here, if we multiply top and bottom by 3 plus 4i, let's think about what we're going to get. And let's consider the denominator first, because that actually shows us why it's such a good choice here. So if we multiply top and bottom by 3 plus 4i, we'll get 3 times 3, which is 9. We'll then get 3 times 4i, or 12i, but then we'll also get minus 12i, so those will cancel out, and then we'll get subtract 16i squared. Now, I squared is negative 1, so that becomes plus 16. And the reason that's a good choice is because we've got no imaginary parts left in our denominator. And numerator, we're going to have to just go through and expand. So 2 times 3 is 6. We're going to then get 2 times 4i, which is plus 8i, subtract 15i, and then subtract 20i squared, which is the same as adding 20. So that's going to be plus 20 there. Now let's simplify what we've got. So 25 in the denominator. The numerator won't simplify quite so much. Well, 26 subtract 7i. Now, rather than leaving your answer in that form, just look, we were asked for it in the form a plus bi, where a and b are real numbers. I should really say that's in the question, but it's implied if you asked for it in that form. So let's now just split that fraction up. I'm going to say it's 26 of 25, subtract 7/25, lots of I. It's fine to leave it as a subtraction even if you're asked for it in the form a plus bi. You could write it as 26/25 plus negative 7/25 I, but this is the conventional way of giving it even if you're asked for that form. The second example I want to look at here is finding the square roots of negative 16 subtract 30i. So you'll note I've said square roots here. When you're looking at real numbers, you'd only ever, most of the time, at least with conventions, you'd be asked for a square root and it would be the positive number or the non-negative number. When we're looking at complex numbers, it doesn't make sense to talk about the positive or negative number. So we're going to have 2 square roots and we're going to want to state them both. So what we want to say is we're going to hope that we can find a number, a plus bi, such that when we square it, we get negative 16 subtract 30i. And we want, in this case, a and b to be real numbers. We can either just state a and b are real numbers, or we can use this set notation where we're saying a and b belong to the set of real numbers. So this word r is representing the set of real numbers. Now let's go through and expand the left-hand side. We'll get a squared. We'll get b squared I squared, which is going to be the same as negative b squared, and then we'll get 2abi, and we want that to be equal to negative 16 subtract 30i. Now, if these two sides are equal, then the real parts on each side must be equal, and the imaginary parts on each side must be equal. So looking at the real parts on each side, the real part on the left-hand side is a squared subtract b squared, and the real part on the right-hand side is negative 16. So a squared subtract b squared equals negative 16. Repeating that trick with the imaginary part, the imaginary part on the left-hand side is 2ab, the imaginary part on the right-hand side is negative 30. So we've now got 2 simultaneous equations in terms of a and b. They're not the nicest simultaneous equations, but they are simultaneous equations nonetheless, and we can go through and solve these. So at this stage, what we're going to try and do is eliminate one of our variables. If we rearrange this second equation, dividing by 2a, we can get b is equal to negative 15 over a. So dividing by 2 gives us negative 15. Dividing by a then gives us negative 15 over a. And then we can substitute this in to the first equation. We'll get a squared subtract negative 15 over a all squared is equal to negative 16. Deal with that squared, so that's a squared subtract. The negative squared here will become positive, so that's just going to be subtracting 225, which is 15 squared, over a squared is negative 16. At this point, it might look like it's fairly nasty, and okay, it's not the nicest equation ever, but let's deal with it step by step. We don't want the over a squared, so let's multiply throughout by a squared. We'll get a to the 4, subtract 225 is equal to negative 16a squared. And now at this stage, you really want to recognize that this is a disguised quadratic in a squared. If we've got a quadratic, we want to make things equal to 0. So we're going to get a to the 4 plus 16a squared, adding 16a squared to both sides, subtract 225 equals 0. And you can use a quadratic formula at this stage. And you might, if you want, even make a substitution y equals a squared if you find it easier to work with a quadratic once we've written as squared. But you could, if you're feeling confident, look to factorize this straight away. And this is going to factorize to a squared subtract 9, a squared plus 25. You can expand that and check. That should work nicely for you. And now we're in a situation as well. So we're getting a squared equals 9, or a squared equals negative 25. Now, if a squared equals 9, we're getting a is plus or minus 3. And here, well, because we're working with complex numbers, we might be tempted to say a is plus or minus 5i. But let's have a look up here. We said we wanted in this form where a and b are real numbers. This doesn't have any real solution, so we'll say reject as a squared is always greater than or equal to 0 when a is real. Just whenever you're rejecting, give a reason. It doesn't have to be stated like this, but I would say that either we need a to be real, so a squared is positive, or something along those lines. Give a reason. You will occasionally lose marks for just ignoring this possibility. As is, we're getting a is positive or negative 3. So now, if a is equal to 3, let's work out what b is. Well, we've got a nice equation for b in terms of a, so we can just substitute that in there. We'll get b is negative 15 over 3, which is just negative 5. And if a is equal to negative 3, then b is going to be equal to 5, doing the same trick. So the square roots and we're just putting this in the form a plus bi, so 3 subtract 5i, and negative 3 plus 5i. And that's our final answer. So just to recap that method, because there's a lot going on in that method, we're setting up an equation. We're saying we want our complex numbers to be a plus bi, so a plus bi squared is equal to this. Expand, equate your real and imaginary parts, eliminate one variable to get a quadratic. You'll always get a disguised quadratic in your other variable in these sorts of questions. Factorize or use the quadratic formula to solve. Pick your real solutions, go back and find your others, and write it in the form a plus bi. Thank you very much.